Hello everyone. Welcome in the subject of mechanical system design of BE Mechanical 2015 pattern. I am Professor A.P. Godke, delivering the lecture on gearbox design, which is applicable for the machine tool. So today we will see the topic design of machine tool gearbox. In that, various laws of step regulation of the speeds in multi-speed gearbox. So, a gearbox, we know it is a mechanical device which is used to transmit the power from prime mover to machine tool by varying the speed or by changing the speed, torque, or by changing the orientation of the drive. So we require the different spindle speeds. So for machine tools like lathe machine, a drilling machine, or milling machine, it required a different spindle speeds. So we have to design the multi-speed gearbox. And if you want to design the multi-speed gearbox, certain laws we have to take into consideration for regulation of the speed or speed stepping. So there are three basic laws of progression. One is arithmetic progression, the law of arithmetic progression. Second one is geometric progression, and third law is harmonic progression. So these are the three laws that are used to perform the stepping of the speeds in case of a multi-speed gearbox. Now, if you look at the difference of these laws, or we will now see the comparison of these various laws of the progression. So first is the definition. So for arithmetic progression, the definition of the arithmetic progression is that the difference between any two successive spindle speed is a constant. The difference between any two successive spindle speed is constant. So that is the definition of the law of arithmetic progression. Means if you take the difference of any two successive spindle speed like n2 minus n1 or n3 minus n2 or n4 minus n3 or nz minus 1 minus z previous value. So that difference is always come as a constant. Such a law of progression is called as a arithmetic progression. Second, geometric progression, the ratio of any two successive spindle speed is a constant. Okay, the ratio of any two successive spindle speed is constant. That law of progression is called as a geometric progression. Means if you take the ratio n2 upon n1, n3 upon n2, n4 upon n3, or n5 upon n4, that ratio becomes constant. So such law of progression is called as a geometric progression. Then third law is a harmonic progression. For harmonic progression, definition is that in harmonic progression, the difference between a reciprocal of any two successive spindle speed is constant. The difference between reciprocal of any two successive spindle speed is constant. So that law of progression is called as a harmonic progression. For example, 1 upon nk minus 1 upon nk plus 1 is the difference, is the reciprocal difference between the reciprocal of any two successive spindle speed. That value is constant. That's why that law is called as a law of harmonic progression. Next is the calculation of the z speed for the different law of progression. So next parameter is the z spindle speed. So for arithmetic progression, z spindle speed, that is nz, is calculated by the formula nz is equal to n max minus n minimum upon z minus 1, where nz is the z spindle speed or highest spindle speed, n max is the maximum spindle speed, n min is the minimum spindle speed in RPM, and z is the total number of speed step. Means if Z is equal to 12, we have to calculate the N12 from N1 to N12 speed. So that is the formula to calculate the number of spindle speeds. In geometric progression law, it depends on the geometric progression ratio value. So if phi is constant, we can calculate the different spindle speed by using that phi, using the phi. So phi is given as a n max upon n minimum raised to 1 upon z minus 1. So this is the formula to get the geometric progression ratio phi. Phi is equal to n max upon n minimum raised to 1 upon z minus 1, where n max is the maximum spindle speed in RPM, n minimum is the minimum spindle speed in RPM, and z is the total number of speed steps. So this is the formula from which we can get the geometric progression ratio phi, which will come as a constant. And after that, we are using that phi to calculate the different spindle speed up to z the value for the spindle speed nz. Next, third law is the harmonic progression. For that, we calculate the z spindle speed by using the formula n minimum upon 1 minus z minus 1 c into n max, where n minimum is the minimum spindle speed, n max is the maximum spindle speed, z is the total number of speed steps, and c is the constant which we are calculating by using this maximum spindle speed and minimum spindle speed formula. So constant value, if we have a n minimum and n maximum, and if we have a total number of speed step z, then we can also get the c value. So for c value, nz becomes n max here. So we can put that nz becomes n max. We can calculate the c value here. So once you get the c value, by putting the various values, we can get the z spindle speed. So these are the formulas for the arithmetic progression, geometric progression, and harmonic progression, for which we can get the different spindle speeds. So next parameter for the consideration of the difference or comparison is the good or bad or poor. So for arithmetic progression, it is a good in high spindle speed range. Means if we design the gearbox with the arithmetic progression, it will give the good performance at high spindle speed range. Then in case of geometric progression, it gives the good performance in the high spindle speed range. And in case of harmonic progression, it will give the good performance in low spindle speed range. Means if we are doing the speed stepping by using the arithmetic progression, geometric progression, or harmonic progression, we'll get the good performance in high spindle speed range for arithmetic progression, good performance in high spindle speed range for geometric progression, and good performance in low spindle speed range for the harmonic progression. Next one is a poor parameter. So the arithmetic progression is a poor in low spindle speed range. Then geometric progression is also poor in low spindle speed range, but harmonic progression is a poor in high spindle speed range. So it means that the gearbox design with the arithmetic progression, it will poor performance in low spindle speed range. Gearbox design with the geometric progression, it will poor performance in low spindle speed range. And gearbox design in harmonic progression, it will have a poor performance in high spindle speed range. So this will give you the clear idea about the comparison of various laws of progression. Now we will see one example using that example, how the different spindle speeds are calculated using the use of one law of progression. So here it is a problem statement. Design a gearbox for a headstock to give 16 speed ranging from 50 rpm to 1600 rpm. The power supplied by an electric motor of 10 kilowatt running at 1440 rpm through a belt V belt drive with a speed reduction of 2:1. Calculate the different spindle speeds and draw speed chart. So using this example, we can get the different spindle speed, and we have to draw the speed diagram for that gearbox. What is given in the problem statement, that we have to write first. So the given condition is that we have to design the gearbox for headstock to give 16 speeds. Means total number of speeds we have to calculate as a 16. So here Z is equal to 16. Total number of speeds, output speed should be 16. So Z is equal to 16. Then ranging from 50 RPM to 1600 RPM. Means this is the range of the spindle speeds for the output. So minimum spindle speed is given as a 50 RPM, and 1600 speed is given as a maximum RPM. So here N max is equal to 1600 RPM, N max, and this is a N minimum, which is equal to 50 RPM. So selection of the standard speeds. So maximum spindle speed is a 1600 RPM, minimum spindle speed is a 50 RPM. Total number of speed steps are 16. So using a law of geometric progression, we calculate the geometric progression ratio of 5. So formula is that N max upon N minimum raised to 1 upon Z minus 1. So this is the standard formula for the calculation of the geometric progression ratio 5 using the law of geometric progression. N max upon N minimum raised to 1 upon Z minus 1. Putting the value of N max and N minimum and Z, we will get the 5 value. So N max is our 1600, N minimum is a 50 RPM, and Z we are putting as a 16 RPM. So after solving this, we will get the phi is equal to 1.259, which is equal to 1.25. So the geometric progression ratio phi is a 1.25. So from phi 1.25, standard speeds we are achieved from N minimum to N maximum are as follows. So first speed is always minimum speed 50 RPM. Second speed we get, which is equal to the first minimum spindle speed into the phi value. Means your second speed N2 will be equal to N1 into phi. Means 50 into 1.25, you will get the 63. Next, third speed we get from the formula N3 is equal to N minimum into phi square. Means 50 into 1.25 square, you will get this value 80. Similarly, you will get next value as 100, 125, 160, 200, 250, and so as up to 16th value. Z is equal to 16. So we have to calculate total 16 spindle speed value. So final speed value will appear as a 1600 RPM, which is equal to the maximum spindle speed. So for this formula is used as a, for first spindle speed N1 into N minimum, for second speed N minimum into phi square, for third N minimum into phi square, fourth N minimum into phi raised to 3, and similarly phi 16, N16 is equal to N minimum into phi raised to 15. So from that formula we will get the different spindle speed here. Now we have to develop the structure diagram for Z is equal to 16. So this 16 is divided in this form as the 2 by 2 4, 4 by 2 8, 8 by 2 16. So this will be the division of the Z is equal to 16. Now here first value is P1, second value is P2, third value is P3, and fourth value is a P4. So from this P1 equal to P2 equal to P3 equal to P4 equal to 2. Means all the values of P are same. Then here P1 is equal to 2, P2 is equal to 2, P3 is equal to 2, and P4 is equal to 2. Now for the structural formula, standard structural formula is what? Z is equal to P1x1, P2x2, P3x3, and P4x4. So we have to calculate the x1, x2, x3, and x4 value. X3 and x4 values are also there. So our first value x1 is equal to 1 always, x2 is equal to P1, x3 is equal to P1, P2, and x4. Here it should be a x4. X4 is equal to P1 by P2 by P3. So if you take the product of P1, P2, it will be 2 by 2, 4. P1, P2, P3, 2 by 2 by 2, 8. So here x1 equal to 1, x2 equal to 2, x3 equal to 4, and x4 is equal to 8. Therefore, structural formula becomes here P1 x1 is now 2 1. So P1 is 2 and x1 is 1. P1 x1 is 2 1. P2 x2, P2 x2, P2 is 2 and x2 is 2. So P2 x2, then P3 x3, P3 is the 2 and x3 is a 4. Then P4 x4, P4 is 2 and x4 is 8. So here we have to consider the x4, not x3. So here it is mistake. So x4 is equal to 8. So from this we'll get the standard structural formula. Z is equal to 2 1, 2 2, 2 4 and 2 8. Now this is the structural diagram for the structural formula 2 1, 2 2, 2 4 and 2 8. So here number of horizontal lines, that lines are called as the speed lines, which are equal to the Z value 16. Number of vertical lines, which are equal to the number of shafts. So 4 stages are there, 1 2 3 and 4. So 4 stages are there, so number of shafts are 5. So first will be input, last will be the output, and in between 3 shafts are there, that shafts are the intermediate shafts. Now this is the step number 1. Step number 1, or it is also called as the stage number 1. So Z is equal to 2 1. Means you have to draw the 2 lines and spacing should be 1. So here at the center symmetric, we are calculating the midpoint on the input shaft. Then we draw the 2 lines. So 2 rays are there, 2 lines and 1 spacing. So we will get the 2 lines and 1 spacing. For next step or stage, here we have to draw again 2 lines and spacing should be the 2. So here we draw from this input 2 lines and spacing are 2 spacing. This is spacing 1 and this is spacing 2. So for this single we are drawing again 2 lines and spacing is 2. And again for this 2 lines and 2 spacing. So this is for this stage 2 2. Next one is a 2 4. So for these 4 points acts as an input and next acts as the output. So here we have to draw again 2 lines and spacing should be 4. So first line and second spacing 1 2 3 and 4. So here we will get the second array. Again for this 2 lines and 4 spacing, for this 2 lines and 4 spacing, and for this 2 lines and 4 spacing. So in this way we can draw the speed diagram for the 2 4 step. And last step is 2 8. Means we have to draw the 2 lines from each of these node on the intermediate shaft and output shaft. All the nodes should be covered by that conjugate rays. So 2 8. So we have to draw the 2 lines and the spacing should be the 8 between the 2 lines. So first line is this one and second line is this one, and in between the 2 lines we are having the 8 number of spacing. So spacing 1 2 3 4 5 6 7 and 8. So we draw the 2 lines and 8 spacing. For this point also 2 lines and 8 spacing. For this point 2 lines and 8 spacing. Similarly for all the points or last point, these are the 2 line and 8 spacing. So you can observe that we'll get the 2 8, that is nothing but P4 X4 stage. So for last stage all the nodes on the output shafts are going to covered. So this diagram is called as a structural diagram for the structural formula 2 1 2 2 2 4 and 2 8. Once we develop the structural diagram, we can draw the structural diagram by introducing the one more shaft, which is a motor shaft, one more shaft, which is a motor shaft, and one more horizontal line, which is a motor line, motor speed line. So here 1600 RPM is the motor line, but motor speed is not given as a 1600 RPM. It is 1440 RPM. So it will be the below the 1600 RPM. So here somewhere motor speed is a 1440 RPM. So that motor shaft is now connected with the input shaft, and input shaft again a lowermost node on the second shaft, third shaft, fourth shaft, and last output shaft. So this diagram is called as a ray diagram. Then whenever we are combining the ray diagram and structural diagram, it will give us the speed diagram. So we are putting the different spindle speeds on the output shafts. Here from lower side, minimum spindle speed, second, third, fourth, fifth, sixth, seventh, eighth, 9, 10, 11, 12, 13, 14, 15, and 16. So total speed is we are achieved as a 16. Means from minimum spindle speed to maximum spindle speed, we are getting the different spindle speeds by using the speed stepping of the geometric progression. So this diagram is called as a speed chart. So whenever we are considering this diagram from this position, it will be considered as a array. It will consider as a structural diagram. Whenever we are consider the input shaft and lowermost rays, then it will be the ray diagram. And whenever we are combining the both the diagram, such a diagram is called as a speed diagram. So here it will be the 2 1, then 2 2, then here 2 4, and here it will be 2 8. So this diagram is called as a speed chart. So from this lecture, what we learn? The different laws of progression, that is arithmetic progression, geometric progression, and harmonic progression, and how the different spindle speeds is calculated by using the one of the law of progression, and how the structural formula is developed, how the structural diagram is drawn, and how the ray diagram and speed diagram is drawn for the given structural formula.